So again, good morning all. This is recorded. All right, moving on to thermophysics this morning. So we're going to start reading from the handout. Now it's mostly a reading topic. We only have two sections where we have calculation. So just keep up and read us out. Right. If the handouts have not been uploaded, I'll upload it right afterwards, but you can just follow and read. Today is mainly reading. So thermal physics. Thermal physics tells us about heat. So let's read. Let's see if we can go a little closer to the screen. Bueno. Right, so heat is one of the most widely used forms of energy. It is easy to harness and identify. We always know when something has too much heat, meaning it gets hot, or it's lacking heat, it gets cold. And it's very easy to determine changes in temperatures because when it's 30 degrees outside and if it's 32 degrees outside, we know the big difference in those two temperatures because we can feel it. Right? Likewise, in the evening or in the nighttime, if it's 25 degrees Celsius, it's nice and cool. When it drops to 22, we want to pull every single piece of cloth we have from the cupboard. And just 3 degrees difference. So we know how to identify when heat is missing, being lost, and when heat is being gained. So let's continue reading. One of the first forms of energy loss in any system is heat loss. As in the most obvious heat energy loss, the first energy loss we always consider, this is why you're always going to consider heat loss now, especially when you reach Form 6, heat loss as a source of error, as something that takes away energy from your system, right? So anytime we deal with a system, anytime we have to look at how energy behaves, law of conservation of energy, our first suspect or key of missing energy is heat loss because all that excess energy is lost first thing to heat. Remember, we went through this in atomic physics, as in the way how the universe works, everything wants to occupy the lowest energy state possible. And everything it does is hopefully in the process of occupying that lowest energy state. And guess what? To occupy the lowest energy state means we're going to have to get rid of energy. How do we get rid of energy? The first way, the first one here is to give off heat. So continue reading. We shall look at the effect of molecules on heat, the effect of external factors, heat transfer methods, and heat energies. Kinetic theory of matter. All right, now the kinetic theory of matter was the big physics topic in the early 1900s. At the same time when they were doing atomic physics, cracking open the atom, kinetic theory of matter was the biggest topic on the same side as that. As in, even Einstein did some work on it. All right, really, really big topic because they understood that heat, the source of heat came from atoms. Way down in the atom and how atoms behave. And we saw that, right? So according to the kinetic theory of matter, this is the kinetic theory of matter, guys. All matter, it is made up of tiny particles called molecules, and these molecules are always in motion. So this is our kinetic theory of matter. Of course, this is the simplified version. All right, you don't need to go and learn the big complex version, but this is a simplified version. And this is what we have. All matter is made up of tiny particles. Duh, we know that. It's kind of obvious, but this was devised in the early 1900s. So they were still learning about everything, how matter was built, how everything behaved and interacted with each other at a cellular and molecular level. Right? So all matter made up of tiny particles called molecules, and these molecules are always in motion because for things to move, they must have energy. Anybody can tell me what is the equation that relates energy to motion? Anybody want to give it a try? Anybody? How do you think energy is related by motion? There's an equation that we did in mechanics.
E is equal to mc squared.
Say that again. Mechanics and atomic physics. You're kind of there. Right? You all remember kinetic equation, the kinetic energy. We call kinetic energy and kinetic theory of matter for a reason, right? This is where we relate it to each other. Right? All physics can relate to each other in some form or fashion. What they know, we know that when something is moving, it must have energy, and we need energy to move. So all matter are made up of particles, and these particles must be moving because they have some sort of energy stored within them. Simple, simple. Here we're gonna have some abstract thoughts to think about. It's not too hard. So let's continue reading. Once they are moving, they will have kinetic energy, and this energy will present itself as heat. Easiest way to look at energy or energy being given off is the presence of heat or the lack thereof. The kinetic theory has been used to explain states of matter, Brownian motion, diffusion, osmosis, and surface tension. So we're going to go through very, very briefly a few of these because you know how a few of them work already in detail from biology, especially. So we're going to go on to our states of matter. There are three states of matter. Well, at physics level, for your level, there are three, but they're actually four states of matter. All right, so the three that we use in school that we can look at and identify and interact. Why is it moving? Am I touching anything? No. All right, solid, liquid, and gas. There is one more state of matter that we do have. It's called plasma. No, it's not the plasma that makes up your blood. It's plasma, which is very, very hot material that behaves like a liquid and solid, but are not liquid and solid. Plasmas are basically the material that make up fire, basically the material that makes up the sun, as in that type of material, very, very, very superheated material, is plasma. No, it's not melted metal, right? Because you know when we have a flame, that just that little core part is plasma. But we don't look at this anywhere in secondary school at all. Actually, I didn't even look at plasma in university. That's a specialized kind of topic. We will look at the behavior of the atoms in our states of matter. So we have solids. Seriously. A solid substance has strong attractive forces that exist between the atoms and molecules. These forces hold the molecules close together in a regular structure. The molecules vibrate but cannot move or change positions. A solid has a definite shape and volume. So these are what helps us to define a solid. One, it has a definite shape, has a definite volume. We can measure sometimes the actual volume. Well, actually, all times you can measure the volumes. We can describe its shape perfectly. What happens in a solid, because these atoms move they're always in motion. As long as they have energy, those atoms are going to be in motion. What they do, because they're held together in very strong bonds, all they can do is just vibrate a little bit. Okay, not a little bit, vibrate being moving many, many, many times a second, the part where they kind of hum. So they move very, very quick, very, very fast, but they only vibrate within the lattice. So that's all it does do is just vibrate. They're not allowed to move. They don't have the ability to move because they're held together in a very rigid bond, very, very rigid bond. So they're not able to even flex. They're held together very tightly. And that's why solids are nice, organized structures. If you ever look at pictures of um, the atomic structure or the crystalline structure of the solids, they're very organized in sheets or in rows or in little hexagon bonds and whatnot. Very, very, very organized structure, very concrete structure if you want to see. So what we have here, oops, wrong pen, right? A solid has a definite shape and volume. The molecules vibrate but cannot change position. So let's move on to liquids. The molecules are again close together, but they can still vibrate to and fro. They have enough energy to prevent the attractions from holding them in fixed positions, meaning these molecules, they have enough energy not just to vibrate to and fro, but they can move back and forth, right? They can move back and forth, right? So that's how they end up having real nice flexible bonds, right? Those bonds can move all over, allowing them to, to have a not very definite, to not have a definite shape. A liquid will have a definite volume, that is for sure. A liquid has a measurable volume that does not change, but the weaker bonds allow for them to have no given shape. What does a liquid do? It takes the shape of the container that it is in. So a nice little one, what happens in liquids? Liquids have very, very strong intermolecular bonds, meaning the bonds that hold individual molecules are extremely strong. They're usually all covalent bonds, and we know covalent bonds are nice, solid, good, strong bonds. But when we have liquids bonded together, so let's use our most well-known liquid. Y'all, what is our most well-known liquid? Anybody? I kind of giving it away on the screen.
Yeah.
Right? Water, H2O. Most common liquid we have around. Now, liquids have very, very strong intermolecular bonds, meaning the bonds that hold this water molecule together is very strong. I mean, if you boil water, no, we're not causing the water molecules to break, as in the H2O bonds to break. What we are breaking the very weak bonds that bond one H2O to another H2O. That's all we're doing, right? It takes a lot of energy. I tell you, a lot of energy to break a water molecule. Read it up if you want. How much energy it takes to break water into hydrogen and oxygen. I've heard somebody say something extremely stupid, and it wasn't their fault that they're stupid, right? People think that water has oxygen, breathable oxygen, because of the oxygen in H2O, right? Water is a molecule. H2O is a molecule that's bonded to each other. H2O is very different from oxygen. Oxygen is what we breathe. This is breathable oxygen. This hydrogen and oxygen are bonded together. It's not available for us to breathe. So there's no way you can go underwater without breathing apparatus and breathe. Anybody wants to say why fish can breathe underwater then? Anybody want to make a guess?
Have dissolved oxygen in the water.
It has what?
Dissolved oxygen.
Dissolved oxygen in water. Lots of people, you would not believe this, that they really don't know that water, even though it has oxygen, does not have oxygen available for us to breathe. To get oxygen in water, what they end up having, they have H2O, they have O2 that is dissolved in the water, because what happens, there are spaces between these water molecules that we can go and hold gases. So if the water molecules are very, very strong, we said that they are very strong intermolecular bonds in water, but water must have a weaker bond. They say they have weaker bonds, right, that hold the water molecules together. So what ends up happening? We have a very, very weak bond that holds water molecules together. Anybody knows what this weak bond is called? It's a chemistry term. It's two words. What's a very, very weak bond in chemistry?
Van der Waals
Van
attraction.
der Waals forces. Very good. Van der Waals are the very, very weak bonds that hold water molecules together. And that's why we're able, when we boil water, we can break these very weak bonds and create water vapor in the gaseous form or steam. So it's because of these very, very weak flexible bonds, water does not have a given shape. You can take the shape of whatever we put it in because it's flexible. Think about it as plasticine, right? We can take plasticine and mold it into a shape because those bonds are flexible. Yes, we do have the theory that cats are also water molecule, liquid molecules. Anybody ever heard of that? Cats can be considered to be liquid. You all never heard of that?
No.
No? You all see the wrong memes, man. Right? Why they say cats are liquid? Because what we have, they can basically take the shape of anything they are in. Y'all tell me if this look true. Cats are liquid.
Okay, yeah.
You can drape a cat over something. No, they're dogs so much. And a cat can take the shape and size of a container that sits in. So cats are liquid. Physics, that's very wrong. Biology, that's very wrong. But in practicality, yeah, I agree. Y'all, that's a liquid to me. Right? Cats are liquid. So if you've never seen that meme, go look it up. There are tons of them. I think I have one with physics formulas in it, right? To show that a cat is actually a liquid. Y'all miss out on you see, I know the nerdy memes. A cat is a liquid. Look at it. Fits in the container. And I'm sure you could take that tail and tuck it in and it's going to take up the whole container. Anyway, let's move on. Gases. The molecules are well spaced in a gas, meaning we have one molecule here, we have a next molecule here, a next one quite far away in relative positions to each other. They are so far away from each other that they have enough energy to be virtually free of any attractions between one another. So this molecule is by no means attracted or influenced by the next molecule and is by no way attracted to the next. They're too far away to influence each other. They travel at high speeds and may also spin. So, like before, remember we had solids that are locked in a solid bond, can't go anywhere. All they can do is probably vibrate a little bit. Water, nice flexible bonds, right? And gas, one bond here, one bond there. They probably spin around in the air, they vibrate in the air, they travel very fast and anywhere they want that they can travel. Unlike liquids and solids, they have no exact volume nor shape. Now, this is a problem here. Gases, this is why we had a kinetic theory. There was a big issue regarding how do we treat gases because gases do not have an exact volume. You all know we can compress a gas and turn it into a liquid, right? You all should know this by now. I hope. Anyone here ever wondered how we get liquid oxygen? How we have liquid nitrogen?
No, I never think about it.
But we all know that is how they transport oxygen to hospitals, to industries. They transport it in the liquid form because the amount of oxygen that you require for these places, you need to carry a lot. And if you were to carry gas oxygen, the summer you're going to need hundreds, thousands of trailer trucks to carry these. Right? They had it just this morning. Right? I think I saw it in Facebook this morning. That Saudi Arabia was sending oxygen to India And when we hear how much oxygen that they sent, you will not believe how much oxygen was contained in this truck. Let me show you this image. You all give me a guess. As in, when they expand this oxygen, because it's right now in liquid form, when they expand this oxygen, it's going to end up becoming, look at this, right, guys? Anybody wants to guess how much equivalent oxygen this truck has? And you all look at its size of the wheels. You know it's not a very big trailer. How much oxygen this is? Anybody want to guess? This truck carries the equivalent of 20 tons of oxygen. You all know how heavy a ton is, right? This doesn't look like 20 tons, right? 20 tons of oxygen. So what we do when we cool down a liquid, we force the molecules closer and closer and closer together. And when we force them closer together, guess what? When we have one oxygen here and one oxygen here, if you look in the video, when we bring them close enough together, we end up going to push them very close together. So the point where they're no longer individual molecules, they're now going to start to bond with each other by van der Waals, of course, right? And create a liquid. So when we freeze gases, it becomes a liquid. Now we're talking about gases that are gas at room temperature. So oxygen is a gas at room temperature. And the only way we can turn it into a liquid is to take it in a big container. So we take a big container, fill it of gas, and then we start to pressurize it. We start to squeeze it essentially from all sides till it changes from a gas to a liquid. Right? So all these gases that we use in industry and in medicine, right? Liquid nitrogen, we all hear about liquid nitrogen. They use that to fill the balloons, right? Or the big aluminum mylar balloons, right? Liquid oxygen, we know that's for providing oxygen in hospitals and in industry. Liquid hydrogen and helium. We know they use helium to fill balloons, and people do that funny balloon voice. All these gases, you can compress them down to a liquid, right? And what that ends up telling us, because we can squeeze a gas and change its volume, that's why they say that gases have no exact volume. What they do have, gases will occupy the container that they are in. Only when volume is small enough, the gas molecules will constantly collide with each other, which will lead to the formation of bonds to become a liquid. So generally, gas molecules are very far apart. They're moving extremely fast. They'll probably, if they're going to interact with another molecule, all they'll do is just bounce off the next molecule, if they happen to bounce into another molecule. Because remember, molecules are very, 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 very small. And think about, if in comparison, a room to the size of a molecule, you're looking at something that is trillions and quadrillions times larger. So the chances of one molecule hitting another is very small. Brownian motion. You all should know this from chemistry. You all know this from chemistry or bio? Bio. During an experiment with pollen grains in water, it was observed that pollen had random motion. They noticed, we know the Brownian motion experiment. The explanation was due to the interactions of the moving water molecules and pollen grains. But Brownian motion can also be seen with smoke molecules and their collision with air molecules. You know, as a next good way to see Brownian motion in the air, you all ever realize, like early morning, if you stand up to the side of the window, right, and a stream of light is coming in, can't you see the dust particles in that stream of light? Early morning, we're talking about. For those who get up early in the morning and just stare at the light coming out of a window, you know, this is how scientists do things, you know. We don't just stare aimlessly in space. Okay, yes, sometimes we do because we're tired. All right, but we stare at things, we look at things, and we realize, wait a minute, something's happening there. So next time, y'all, if there's happen to be smoke, or best thing, just dust out anything in the room because we have a lot of dust. Right by your window in the morning or wherever is getting early morning rays coming through the window. And if you look, you will actually see the random dust particles just floating in the air. Take a look next time there's bright sunlight in the morning, right? And there's probably a little crack in the window, not the window, a little crack in the curtains or whatever, so you get a pure stream of light passing through. You'll be able to see Brownian motion of dust particles in the air. Diffusion. See how I said physics is everywhere? It is everywhere. Diffusion. You all know of diffusion. This is chemistry and biology too. It's essentially traveling from low concentration to from high concentration to low concentration. I'm not even going to go through that. You all could read up on diffusion. Similarly for osmosis, this is a biology term and a chemistry term, right? What we use osmosis for mostly in physics is to get pure water out of salt water or out of any other type of water. So you all can read up osmosis. You all should know osmosis in diffusion and no in bio and chem. Temperature. Temperature is a quantity used to measure the amount of energy a system has. As in, there is a direct correlation and a direct relationship between temperature and energy in a system. And since there is a direct relationship, we use the amount of energy to record or to determine our temperature. There are many temperature scales that are used in regular life. In physics, the SI unit of temperature is used, which is the Kelvin scale. The Kelvin scale is brand new to you all. We know regularly, we use the metric system, right? We use the metric system, which is based on a decimal set of count, meaning we count in tens and in hundreds and whatnot. So that's why we use the metric system. And we know the metric unit for temperature is what, folks? What's the unit for temperature? What do we measure temperature
Degrees
in?
Celsius.
Degrees Celsius. This is what we use. We use the metric scale. We do not use imperial scale. So if anybody happens to see degrees Fahrenheit, we don't use that again. We used to use it long ago, like 50 years ago, right? Because that's when everybody had the imperial scale. Imperial scale is the other old scale. We don't use degrees Fahrenheit at all, ever. All right, and there's a long, to convert from degrees Celsius to Fahrenheit, you have to multiply by a number and then add a next number to it. It's a formula, it's a weird, funky formula. So if you want, you can go and read it up how to convert from Fahrenheit to Celsius. But what we're going to do today in physics, the scale that we use most times is Kelvin. Not all the time we use Kelvin. It's not necessary to use Kelvin all of the time. But for some of these topics, Kelvin scale is what we are going to use. So let's read what the Kelvin scale is. Please note it is not degrees Kelvin. It is not degrees Kelvin. It is just Kelvin. Of course, it's named after the guy, something Kelvin, Lord Kelvin, actually. Yeah, Lord Kelvin. The Kelvin or absolute scale, it's called the same thing. So if we're referring to the absolute scale, we're also referring to the Kelvin scale, is a measure of the amount of energy a system has. There's a point when an object can lose all its energy. So there is an absolute zero. There's something that we can reach. There's a limit to how cold something can get. Even down to the atoms, they cease to vibrate and move. This is called absolute zero, otherwise known as 0 Kelvin. You're going to get mixed up. This is okay, and this is 0 Kelvin. Sorry. We'll just have to figure it out. All right, so 0 Kelvin is the coldest anything could possibly reach. So there is a limit to how cold something can get. There's no such thing as minus a million degrees Celsius. No such thing, right? Because because what they did work out, and it's by mathematics, of course, because they didn't have the equipment back then to freeze something to 0 Kelvin or to get to 0 Kelvin. Up to now, we can't get to 0 Kelvin. Up to now, right? But they did work out the maths and they realized that the coldest something could possibly get, which is 0 Kelvin, is minus 273 degrees. Well, it's actually minus 273.11 something, 15, 14. Okay, I'm mixing up this last number. But 273 degrees Celsius is the smallest or the lowest possible temperature that can be reached. Why? Heat is a measure of energy, and we can pull out all of the energy out of an atom and make everything stop moving, as in freeze it completely. When we talk about freeze it, that means the electrons are no longer moving. That means the protons are no longer vibrating to and fro in the atom. That means all of the little small subatomic particles have stopped. Everybody has stopped, has frozen, right? Because we have pulled out every single ounce of energy that is there. Now, theoretically, it is possible to reach 273 degrees, but to actually pull all of the energy out of an atom, to make every single particle stop moving, right now is still kind of impossible because we don't have the know-how or the technical know-how to pull out every ounce of energy from something. All right, so what we have here is 0 Kelvin is equal to minus 273 degrees Celsius. So if I were to plot a graph of energy, why don't I have that other graph? So if I were to plot a graph of energy, all right, that's our energy scale, our energy axis, versus temperature in Kelvin, what I would end up getting, I would end up getting a straight line graph that starts from the origin. So what I'll end up having, I'll have this happening. If I were to plot a graph, let's get exactly in the middle there. All right, looking like this. If I were to plot a graph of energy versus temperature in Kelvin, I will have a graph that starts at the origin because I have no energy at 0 Kelvin. But we have to be able to know how to convert, and this is from this equation, it's from this graph, they determine what 0 Kelvin was because it was a straight line graph. So they can work out what temperature every drop of energy disappears at. So if you convert, how to convert Kelvin to Celsius, this is something you have to learn, right? So if you were given a temperature, any temperature in Celsius, and I wanted to find the Kelvin value, all right, what I'm going to have to do, just now, I think I have that backwards. Why is it looking like that? Go away. All right, let's pull this aside. To convert from Kelvin to degrees Celsius, we have to know that 0 Kelvin is equal to minus 273 degrees Celsius. So if you use the formula here, 0 Kelvin is equal to minus 273 degrees Celsius. No, you're not going to add and subtract a value here. They're related by a number, right? 1 Kelvin will be equal to 1 plus 1 minus 273 degrees Celsius. And that's going to be minus 272 degrees Celsius. So to go from Kelvin, Anytime you're a little confused, all right, that's why I think, I don't know why it's saying like that. All right, to go from Kelvin to degrees Celsius, you're going to have to subtract 273. That's all it is. So suppose I had 100 Kelvin. 100 Kelvin will be equal to 100 minus 273. We're just going to do some examples here right now. Oopsie. Let's put it at the corner here. So from Kelvin to degrees Celsius, you subtract 273. And on the flip side, to go from from degrees Celsius to Kelvin, we will add 273. So all we're doing is just adding a number. So let's go through and give a try here and see what we can get. All we're doing is just subtracting a number and adding a number. So suppose my temperature in degrees Celsius was 0 Celsius. What is my temperature in Kelvin going to be? We're going from Celsius to Kelvin.
273.
273. All we're doing, anytime we have to convert, we're not multiplying anything. Yeah, right? All we're doing is just adding a number when we're converting from Celsius to Kelvin. And when we're converting from Kelvin to Celsius, we just subtracting a number. That is all. Add and subtract. One is the reverse of the next. So let's say if I had 27 degrees Celsius, what is my temperature going to be in Kelvin? You all can put it in the chat too if you're feeling shy. Or your mic not working.
299. 300.
300. Very good. 300 because 27 plus 273 is 300. All right, you're going to realize this is a very common number you're going to get in your questions, for nice conversions. Like, suppose my temperature is 150 degrees Celsius. What is my temperature in Kelvin? Get out the calculators or work it out by hand, whichever one. How much? I didn't hear you. Put it in the chat.
323.
300. No, not 300.
323.
You said 323?
Yes, miss.
No. Try it again. Somebody else. Anybody else? Yeah, you can put it in the chat if you wanted. Very good, Isis. Correct. All right, because the 150, you're going to add 273. 3, 2, 1, 423. So to go from Celsius to Kelvin, we add a number. And on the flip side, this is where people get a little scared because they start seeing negative numbers. Remember, don't be afraid of negative numbers. In physics, we have negative degrees Celsius. Suppose I want to go from Kelvin to degrees Celsius, right? Remember what we do? We subtract the 273. So suppose my temperature in Kelvin is 500 Kelvin. What is my temperature in Celsius?
The 27.
227. Very good. Oh, let me write that down better rather than something waiting in space. 227. 100 Kelvin was my temperature.
Minus 173.
Minus 173. Very good. 3 Kelvin.
Minus 270.
270. All right, now just random knowledge. 3 Kelvin is the average temperature of outer space. Outer space is not 0 Kelvin because there's energy left over from all the interactions, all the events that have taken part in the universe so far. That temperature still remains, right? And it's transmitted and radiated throughout the universe. And they worked out or realized that the average temperature of outer space, meaning everything out there beside planets and asteroids and comets and all of that other stuff and stars, is 3 Kelvin. So that's the average temperature of outer space. In case you ever thought about it or never thought about it, now you're thinking about it. I don't know space had temperature. There is a temperature in space. So please note it, how to do it. Celsius to Kelvin, you add, and Kelvin to Celsius, you subtract. Remember one, and once you remember one, just know that the other one is the opposite. Opposite of addition is subtraction. So let's finish up here. Yeah, we can finish this in about 5 minutes. Thermometer calibration. I am sure you all know about the thermometers we use in school or use generally. They have equally spaced markings. Those equally spaced markings are not put there just so. They don't look at the glass and realize, 0 is here and 100 is here. No, they have to calibrate that thermometer, right? And there's a very simple way in calibrating thermometers that we use regularly. So let's read. Really simple way, all right? We have the equipment. It's only if we had gas, we now get back gas. So thermometer calibration. When we have to calibrate a thermometer, which is to put those equally spaced lines on the thermometer so we can actually use it to read a temperature, two values must be known in order to do this. We must know about an upper fixed point and a lower fixed point. This is a multiple choice question. All right, for sure, this comes as multiple choice. I can't say for this here, but what is the lower fixed point? Obviously, lower means smaller. And the smallest temperature we know generally right now is, generally, not in maths wise, is the 0 degrees Celsius. And that is the melting point of pure ice. Pure ice means pure water, not tap water, because tap water has dissolved minerals in it, calcium, phosphorus, dissolved gases, oxygen, nitrogen, air, chlorine. So tap water is not pure water. Remember, you went through this in the lab, right? That water has impurities. Pure water is pure water, meaning it only has H2O, nothing else. No dissolved gases, no electrolytes to have dissolved minerals, no salts, nothing in them. So pure ice or pure water freezes at 0 degrees Celsius and it melts at 0 degrees Celsius. If it has any sorts of impurities, it will not melt and freeze at 0 degrees Celsius. Close, but it will not. So use pure water. Anybody here knows how to get pure water? Easiest way to get pure distilled water. Chemistry, biology. You all never did distillation? Chemistry.
Yeah.
How do you get pure water from distillation?
Use fractional distillation.
Not so complicated, Fractional distillation is for things that have multiple melting boiling points. It's a very simple distillation process. All we do, take some water, boil that water, create steam. We let that steam. So if we have our flame, we have our little container that has water in it. All right, so this is our flame, boiling the water. That steam, we have it trapped in a container, so that steam can travel through your container. The steam is going to travel, and because it reaches the upper end of your glass tube or whatever, it's going to cool down. And when steam cools down, it condensates, and condensation will give us pure water. And that pure water, we can collect it in bottles, or you can just strip down into a container. Simplest distillation, you just boil it, right? And by boiling it, we will collect just pure water steam or water vapor. The steam is going to condensate, and we're going to get pure distilled water. That's why they call it distilled water, because it went through the process of distillation, in case you never thought about it. So that's the melt point of pure ice. And the upper fixed point, which is what I just said, right? The boiling point of pure water under standard atmospheric conditions. Chemistry chair, and again, what is STP? You're writing exams. You should know what STP is. I learned this in Form 4. Come on, Olio, in chemistry. STP.
It's like the value or
No, what it mean?
standard temperature pressure.
Standard temperature and pressure. You all ever happen to learn what are the values of STP? What is the temperature we take and what is the pressure we take?
Most we just learn that at RTP and STP when it's doing moles.
Okay. RTP is room temperature and pressure, and STP is standard temperature and pressure. Now, STP is obviously a more universal phrase because different places have different room temperatures. Trinidad lab's room temperature is far different than the room temperature in Norway or in Alaska or in Antarctica. Very, very different. But standard temperature and pressure is a universal um, agreed on number, right, for temperature and pressure. So I think it's 27 or 25. Let me check. Don't know why I mixed up the two. Right, STP. Oh, RTP is 27 degrees Celsius and 1 atmosphere. And STP is 0 degrees Celsius and 1 atmosphere. Meaning you can freeze down, you could cool down something. Any room or any equipment and experiment is 0 degrees Celsius. Or we can use um, room temperature pressure, which is 27 degrees Celsius and 1 atmosphere. You all should know. Anybody could tell me what's the pressure of 1 atmosphere? We're doing exam just now, revision time. Anybody? How many atmospheres and how many pascals in a atmosphere? So wait for me to draw it out. Eh? Anybody? Uh-huh. You're missing something, Isis. Anyone? How many pascals in 1 atmosphere? You all remember that? That looked familiar. 1.01 pascals are in 1 atmosphere. And remember, 1 atmosphere is the pressure at sea level, which is an accepted value across the planet because we are more than 50% water, right? Sea level is a universal measurement requirement on this planet because we have far more sea level than land level, right? So atmospheric pressure at sea level is 1.01 by 10 to the 5 pascals, and we use this as a defining unit for pressure, especially for gases, right, as 1 atmosphere. So if you ever looked it up before, room temperature pressure is well, there's a standard room temperature and pressure. This is why our labs are supposed to be air conditioned because we must have a specific temperature to do our experiments. Otherwise, we have to factor in the effect of heat. Not all the time it affects it. So don't come here in Form 6 and say, Miss, the lab was too hot to do the experiment. A hot lab is not going to affect how a pendulum swings. Right? But room temperature pressure is a standardized value, as in we assume that our pressure is 1 atmosphere. Yes, right now, okay, we finished with calibration. Yes, right now we are above sea level. I think we're about 50 or 75 meters above sea level. So our pressure is a little smaller than 1 atmosphere, but it's so much smaller than 1 atmosphere. We can assume it to be 1 atmosphere. All right, STP, standard temperature pressure, is just an accepted value. So let's remember it for chemistry and for physics, folks. All right, so we'll continue reading this. Well, not next day. I will continue this on a video. All right, so let's share this. I'll write down where we reach. I'll leave it right here. Stop. Share. Close this off. Right, so as I was telling the class earlier, I know a few of you will join later. My moderation starts from Monday, so I'm going to be out of school for a couple of weeks. But depending on my timetable, if I happen to have, like, say, a Grandi or a Rima school day, I can still teach you all first period and then go to my moderation. So what I will do, I'll just look to see how my timetable matches up with the school timetable. And if I have to leave a recorded session, I will leave a recorded session because this entire topic here will take 4 sessions like this. You know, if we didn't have the interrupted talking in front and back, right? We will have 4 sessions to finish up the entire topic of thermal physics. So I will record the next session and put it up for you, probably this week self, because it's going to be too busy come next week. Hold on. All right, so just to tell you, if you want to go ahead and read the rest of the handout, the rest of the handout is looking at thermometers, the different type of thermometers we have. We're going to look at gas laws, which is one of our big equation section. What is physics without equation? All right. I actually personally get sad when I see physics without equations. Really sad. So that's what we're going to do next day. All right. So next day or next class, you all are going to have me finishing up thermometers and then going on to gas laws. So I will stop the recording there. All right. And if anybody have any questions, we can go through it now.